Laser cooling means shining light on stuff and making it cold. Now that in itself sounds like it's completely backwards, because after all, you typically think if you shine light on something, it's going to get warm. So how is it even possible to shine light on something and make it cold? To cool the air down means to make those molecules, atoms in the air, move more slowly. That's the difference between hot and cold. So how do you make something cold with a laser? Well, lasers, all light, pushes on stuff. There's a thing called radiation pressure. Light pushes on things. What we've figured out to do over the years is how to push on atoms in such a way as to make them slow down. The thing that was perhaps the crowning achievement of the early days of laser cooling was the discovery that we made in our laboratory that it was possible to get these atoms colder than everyone had thought was the limit to how cold you could get something. The prediction said that we could get down to temperatures of 240 millionths of a degree. In other words, 1/4 of 1,000th of a degree above absolute zero. Pretty cold, right? Well, in fact, we got a whole lot colder than that. And that was the big breakthrough discovery that made a whole lot of other things possible. Well, all clocks have tickers. All of these tickers have imperfections. Every quartz crystal is made a little bit differently. The length of the pendulum can change a little bit, and that changes how fast it will swing back and forth. So all of these clocks have imperfections. And so one has, throughout history, been trying to make these clocks better by making the tickers be more reliable. That is, always have the same ticking frequency. Well, it turns out that atoms are the best choice for making tickers that always tick at the same frequency. Even atoms have their imperfections. Temperature means that the atoms are moving with a certain velocity, having a certain kinetic energy. The hotter the gas is, the faster the atoms are moving. It's not so easy to measure the ticking frequency of something that's whizzing around at the speed of sound. And that's the problem that everybody was facing with atomic clocks, was that the atoms were moving at approximately the speed of sound, and it wasn't so easy to measure the ticking frequency. So we said, let's cool them down using lasers so that they're going more slowly, and that'll make it easier to measure the ticking frequency, and you can make better clocks. When I started doing laser cooling, the very best clocks were accurate to a part in 10 to the 13. So that's 1 part divided by 1 with 13 zeros after it. That's the fractional error in how good that clock was. Sounds incredible, right? But today, those clocks are a couple in 10 to the 16, almost 3 orders of magnitude better. And that has been made possible because of laser cooling. I suppose that young children are curious about everything, and very early my curiosity tended toward curiosity about science. My parents got me a microscope when I was very young, maybe 6 years old, and I remember looking at all kinds of things around the house with this microscope. I remember collecting various household chemicals and fluids to mix together, which was my homemade chemistry set. And in addition, I was doing all the other things that kids do, climb trees and scurry up and down cliffs and collect huckleberries in the woods. But there was always a lot of physical activity, and a lot of that physical activity for me involved doing things that related to science, looking at stuff, being curious about the natural world. That's a really interesting question. Sadly, the answer isn't simple. The simple answer is no, but now I've got to explain why I'm saying that the answer is no. The answer is that every process for cooling either also introduces the possibility that you can introduce some extra energy into the system. You see, cooling means taking energy out. And heating means putting energy in. But in order to take energy out, then it turns out that you open the door for energy to go in. Take laser cooling. Laser cooling takes the energy out by having an atom coming along, and then a photon hits the atom and slows the atom down. But then that photon has to go someplace. And when that photon is shot out by the atom recoils and more energy goes in. So there's a balance between the cooling and the heating. And you can try to make that balance work more and more in your favor, but you can never make it work 100% cooling and no heating. So that's one of the reasons why you don't expect to ever get to absolute zero. On the other hand, what does it mean to be at absolute zero? It means that all the thermal motion stops. Well, I can take one atom and I can take as much energy out of it as possible so that it's in what we would call the ground state, the lowest possible state of energy. Is it absolute zero? Not really, because in order to be at absolute zero, I really have to have a whole bundle of things. I can't really talk easily about the temperature of a single object. I should really talk about a whole ensemble. And if I do that with a whole bunch of atoms, what's going to happen is, maybe if I'm lucky, maybe 99% of them are going to be in the ground state, and then 1% isn't. So it's not absolute zero. I can't come up with any procedure that is going to say 100% of the time, this atom's going to end up in the ground state. And that's what I would need to be able to claim that I'd really gotten to absolute zero. But on the other hand, I can get so close to absolute zero that for many experiments, it's basically absolute zero for all practical purposes, but not for all experiments. And we're constantly working on trying to make things colder, because for some experiments, it really matters that we're not quite there. Well, my reaction to hearing about the Nobel Prize was one of shock and disbelief. In fact, I can remember very, very well when this happened. I was attending a meeting in California, a meeting of the American Physical Society and the Optical Society of America, meeting jointly out in California, in Long Beach, California. And the day before the prizes were announced, a number of us were sitting around after the scientific sessions were over, speculating about who was going to get the Nobel Prize that year. And believe me, nobody brought up my name. So later that night, well, it was the middle of the night, that I got a call in my hotel room to the effect that I had shared the Nobel Prize with Claude Cohen-Tanuji and Steve Chu, came as a complete shock. My life changed dramatically. It's very difficult for me to keep up with all of the invitations that I get to speak about my work. The size of my research group has grown. That's made it possible for me to be involved in more and more new kinds of physics, but it's made it harder and harder for me to be intimately familiar with all the things that are going on. So there's a kind of a tension between the joy in doing lots of new things and the desire to understand them better and better. Another thing that I never would have imagined would have been one of the results of becoming a Nobel laureate is that I ended up meeting people who are actually famous. So, people say, oh, you're a Nobel laureate, you must be famous. No, nobody remembers, outside of the field in which you're working, nobody remembers who won the Nobel Prize even a couple years ago. But as a result of being a Nobel laureate, I get invited to things where I've met people who are actually famous. So one of the people that I have met who has been most charming is Dr. Ruth Westheimer. She lives in New York City, and I see her probably about once a year, and she's just a wonderfully warm and genuine person. Just a joy to know as a friend. Well, first of all, I should say that I'm not particularly comfortable with being described as a religious person, because somehow I have this image in my mind of somebody who's very proper and prim and follows all sorts of rituals and stuff. And I like rather to describe myself as a person of faith. And Clearly, I don't believe that science has made belief in God obsolete, or else I wouldn't describe myself as a person of faith. I believe that certain ways of interpreting certain scriptures have been made obsolete by science, but that in no way makes religious faith or belief in God obsolete. It just requires what I would consider to be a different outlook, a maturation of religious faith. But if we look at the history of religious faith as told in the scriptures and as seen throughout history, I think the entire history of faith has been one of a maturation of that faith. I see it not so much as people becoming more mature in their faith, but God challenging people to become more mature, to get a clearer understanding of what God wants for humankind. And I think God is always pushing us to be better than what we are. Okay, so there's two ways of answering that question. By and large, science and religion deal with different kinds of questions. Science deals with questions about how did things come to be the way they are, how should I think about the way things are, how shall I organize my understanding of the way things behave. Whereas religion deals with questions like how should I behave toward my fellow human creatures? What should my relationship be to God? How should I understand the ultimate origins of this world and this universe in which we live? These are very different kinds of questions, but sometimes the areas that science addresses and the areas that religion addresses can overlap. So I don't ascribe to the idea of science and religion as being non-overlapping magisteria, as they've sometimes been described. But I also will say that by and large, they deal with different kinds of questions. But there are ethical questions that might involve things like medical ethics or environmental questions, where you have to understand the science in order to be able to make good ethical decisions that are guided by your religious principles. So there's always going to be places where science and religion are going to come to bear on the same kinds of problems. All the time. In fact, it's one of the greatest things about being a scientist is that you're continually surprised. Nature is so much more clever than we are that we never understand the secrets that nature has to offer. But little by little, we learn more and more. But every time we go into the laboratory, we're surprised. I work in an area of physics, atomic physics, where the basic principles, as far as we know, the basic principles were pretty much understood in the 1930s. Maybe some details were worked out in the 40s and 50s, but we are still surprised every day by the results of these things. So in spite of the fact that some people might say, well, there's nothing new, we're surprised every day, and the things we learn were things that nobody imagined that things would work this way. So for example, let's go back to this example about laser cooling. Everybody thought they understood how cold you could get things using laser cooling. And the problem was a simple enough problem. You can write down the proof in a few minutes as to how cold it's possible to get something. And we got it eventually 200 times colder for one particular atom than the theory said was possible. Why? Well, because the situation was a little bit more complicated. Remember I said that physicists like to make a problem really simple. That's the physicist's way of looking at a problem. Well, Einstein once said, a problem should be made as simple as possible, but no simpler. And sometimes you make a mistake and you leave out some really important stuff. Usually when you do that, it makes things worse. This was a case where putting in the complications made things work better. Nobody would have guessed that that was going to happen. I can't imagine anybody sitting down and thinking, okay, we're going to figure out how laser cooling works and coming up with what actually happens. We had to do the experiments first. Nature showed us what was going to happen, and then clever people figured out what was really going on. These kinds of surprises happen to us all the time.